Good morning, everyone. It's good to see you guys. Today, my name is Noe. That's Moises, and that's Dylan over there. And today we're going to be presenting on Markov chains. So I want to give a quick outline of what we're going to be talking about. So first, we're going to give a mathematical introduction. So that includes like motivation, definitions, terminology, a very important theorem, etc. And then at the end, we're going to give a few practical applications. Also, just a side note, we're going to be switching a few more times during this presentation, so just to give you guys a heads up. Yeah. So motivation, all right, so consider the following morbid example, all right? Suppose that every year, 99% of the people in New York and Florida go to Florida and New York, but 1% from each state die off, right? So we can actually model this using the following diagram, right? And you can see it's very clear. Notice that there's a 1 at the bottom of the death state because 100% of the people who are dead stay dead, you know? But yeah. So we can translate this scenario into linear algebra, right? So the next instance of people in each state is given by the product of that matrix and our vector over there, right? So if we do the matrix vector multiplication, you'll see that it corresponds exactly with the probabilities we said, we just stated, right? And so we can call this matrix P and that last vector yn. If we were to simulate a random walk, that is like a sequence with 50 people in Florida and 50 people in New York, we get the following sequence. So we start 50-50, then it goes to 18 in New York, 18 in Florida, 63 dead. And if we continue on for a very, very long time, you'll see that it seems that everyone will end up dead eventually, right? So now consider a more practical example, right? So suppose any random Barron resident has only 3 places to eat, right? McDonald's, Pizza Hut, baguette. Right? Very practical. Let's say that we have the following like system of complex probabilities over here. So 70% of the people who first ate at McDonald's go to Pizza Hut. The other 30% decide to go to baguette. 60% of the people who first ate at Pizza Hut decide to go to McDonald's. 30% decide to go to baguette, and 10% decide to eat at Pizza Hut again. And lastly, 50% of the people who first ate at baguette go to McDonald's. 40% go to Pizza Hut, and 10% go to baguette again. So just as before, we could model this scenario using the following diagram, right? And here's a question. If out of 100 people, everyone decided to go to McDonald's first, what's the chance on any day that a Barron resident may decide to go to either McDonald's, Pizza Hut, or baguette? And what would happen if instead 50 people started at McDonald's and the other 50 people started at Pizza Hut? So just as before, we have the following matrix equation over here, right, with our corresponding probabilities, right? So how do we determine the number of people in each restaurant yn on day n? Note that yn, it's like a recursive definition here. Yn is equal to p times yn minus 1. But in turn, yn minus 1 is p times yn minus 2, and yn minus 2 is p times yn minus 3, and et cetera, et cetera. And then you get yn is equal to p to the power of n times your initial starting point, and why not, right? So in our example, where all 100 people start at McDonald's, we get the following random walk here. So it seems that it's approaching that there'll be 35 people in McDonald's, 39 in Pizza Hut, and 25 in baguette. But what if we started with 50 in McDonald's and 50 in Pizza Hut? Well, it seems that even though it's different values, like at first, it seems that it's approaching the same vector over there, right? So let's give some definitions and terminology to talk about this stuff, right? So a Markov chain is a system that transitions from state to state according to the probability of any given state happening, right? So a state is a choice or option in a Markov chain. For example, McDonald's, baguette, or Pizza Hut, right? So given the probability yi of a state A occurring, we are able to deduce the next probability yi plus 1 of state A occurring. For clarification, I itself is not the state, it's simply the time that the state takes place, right? Or the probability for the state to take place, right? Lastly, a random walk in the Markov chain is a sequence of probability distributions y1, y2, etc., given some initial starting point, y naught, right? So we already looked at a few random walks and Markov chains just now, right, in our examples. So regardless of our choice of random walk, we saw that they always converge to the same distribution, the same final state, the same y infinity, right? So remarkably, this is true regardless of any initial distribution y naught you start with. If a Markov chain converges, it will always converge to the same final distribution, y infinity, right? So if a Markov chain converges, we call this final distribution, y infinity, its steady state distribution, right? So the information encoded by the steady state distribution tells us the limiting distribution of the Markov chain. That is, it conveys the trend of the Markov chain and how it will converge to equilibrium, provided that it does converge, right? Some more definitions over here. So a matrix P, which is n by n, is called a Markov matrix if all of its entries are non-negative, right? So at least everything 0, and the sum of the entries in each column is 1, okay? So the steady state eigenvalue, which we call lambda 1, of a Markov matrix P is the eigenvalue lambda 1 equals 1. It has a corresponding eigenvector v1, or the steady state distribution. And in fact, y infinity from earlier will distribute according to the probabilities in v1. More particularly, y infinity will be some multiple of v1, right? So given a Markov matrix P and initial state y naught, v1 is the vector such that p to the infinity, that is the convergence of p, times y naught equals v1, as long as Pn converges as n goes to infinity. Furthermore, we have that in particular, P converges to the matrix with V1 as its columns, okay? So there are also different types of Markov chains depending on time. So on the left, we have the discrete Markov chains. That is, you start at 0, and you go from natural number to natural number to natural number, and you can end either at n, which is a finite chain, or an infinite chain, and you go all the way up to infinity, right? Likewise, we also have continuous Markov chains. So each index n is a real number from 0 to r. So all the real numbers from 0 to r, that's a finite chain. And likewise, infinite chain, all the real numbers from 0 to infinity. A slight caveat, you could also start from negative infinity to infinity for infinite continuous Markov chains. It should be no surprise that the type of Markov chain impacts whether it has some steady state distribution. In other words, it influences the convergence. Clearly, for the finite chains, you're going to converge to that last value over here, which is in this case, which is n, in that case, which is r, right? At any finite Markov chain surely converges, which isn't the case for all infinite chains. Some have a steady state, whereas others do not. Finally, there are some special cases, right? So a self-contained or absorbing Markov chain is one in which at least one of the states has a recurring probability of 1, called the absorbing state. And in our New York, Florida death example, death was the absorbing state. Next, we have an ergodic Markov chain in which none of the states are absorbing. Therefore, we have a potential for one single steady state distribution.
All right, so up to now, we've gone over a lot of different definitions and terminology around Markov chains, but you might still see that there's some problems with these definitions, right? They seem a little bit unsatisfying. Who says that the information in these Markov matrices actually encodes the probability of these real-life situations? So that's one of the insights we'll be making in this section. We're going to be showing that, yes, we can actually encode these probabilities into a matrix, and then that matrix will in fact meet all the properties of a Markov matrix. So to do this, we're going to start by considering two states, states A and states B. Each one will have some probability of going from itself to the other, as well as the probability of remaining at itself. So we're going to denote P11 is the probability of starting at state A and going to state A, or remaining at state A. P21 will be the probability of starting at state A and going to state B. P12 will be the probability of starting at state B and going to state A. And lastly, P22 will be the probability of starting and remaining at state B. Next, we're going to also consider an initial distribution we'll call Y0. It's going to be an initial value of A and an initial value of B. So if we want to determine the next distribution, Y1, according to the probabilities above, we must simply calculate A1 as equaling A0 times P11 plus B0 times P12. And likewise, B1 will equal A0 times P21 plus B0 times P22. Now, if you're still a little bit unsure that these definitions are true, let's take a look at our diagram. So given that we have an initial distribution, A0, B0, we can find A1 by taking A0 times P11. It's going to be all the stuff that started in A in our initial distribution and remained in A. plus all the things that started in B0 and times P12 and went to A. And likewise, we can follow a similar thought pattern in showing that B1 does in fact equal that. So if you start to have PTSD at this point, it's because this is pretty much what we've been doing for a lot of the semester. It's just matrix vector multiplication. What we're doing is we're storing our Pij values into a special matrix P. Then we're allowing our initial distribution to be a vector y of 0. So we can rewrite this scenario as matrix P times y of 0 will equal y of 1, the next distribution. And we see that there's something very interesting and very special going on here. So let's take a look at that and give another definition. So we're going to call matrix P, which will be an n by n square matrix of real values. We're going to call that a probability matrix with n states if every value of P, Pij, represents the probability of moving from state j at time n to state I at time n plus 1. Then the probability of any given state will be determined only by the previous state and can be represented by the following equation, which we can simplify to this part on the right. The probability of that y plus 1 equals j, given that y of n equals I. So we see that there's a very strong form of a recursive nature here, and we can always figure out the next term given that we have the current term. So with this definition of a probability matrix in mind, let's look at the example that we went over earlier with the 3 restaurants. So there's our matrix P. We see that each entry does in fact represent the probability of changing from state j to state I at time n to n plus 1. Therefore, we must be able to call it a probability matrix. This means that given any distribution, y of n, the following formula will always hold true in finding the next distribution. Furthermore, we can also see that the probability matrices must also meet the following 2 criteria. First, every entry must be greater or equal to 0, as each one just represents a probabilistic change, which by definition must be between or equal to 0 and 1. Next, that the column, or the sum of the entries in each column must equal 1. And we can see that, looking at our matrix P from before, that is true. Each column sums to 1. Therefore, we can see that all the characteristics are met, and we can say that P is in fact a Markov matrix.
So we've had a bit of discussion on some terminology, as well as we made the key insight that these probability matrices that we're seeing, these matrices that store our probability, are in fact these Markov matrices, right? What we're going to do is we're going to now look at a key theorem that dominates the subject and kind of allows all of the claims that we made, particularly about the steady state eigenvalue and the steady state distribution, to actually hold true. So we're going to look at this major theorem, the Perron-Frobenius theorem, but first you have to just define the following terminology. So we define a matrix to be positive simply if all of its elements, if all of its entries are strictly positive, that is greater than 0. And then likewise we define a matrix to be non-negative if all of its entries are just not negative, so at least 0. Then we can look at this theorem. This is actually Perron's part of the theorem, and Frobenius works for non-negative matrices. Perron looked at the positive matrices. So the theorem states that given some square matrix that's positive, let capital lambda denote the set of eigenvalues of A. If we look at the largest of these eigenvalues, which we'll denote as lambda max is the largest eigenvalue of A, and then it will be real and greater than the magnitude of every other eigenvalue, strictly greater than. Additionally, the corresponding eigenvector to lambda max will be strictly positive. All of its entries will be positive. Now we're going to get into the proof of this theorem. So the way it's going to work is we're going to look at some inequality and then obtain a contradiction, which is going to help us make a big stride, and then we'll be able to finish it off and determine basically what the theorem is saying. So say we have some positive matrix, and we're going to look at this inequality. Suppose we have A times V is greater than or equal to T times V, and we're going to consider this for all real values of T, right? Now, we're going to show that the largest of the values of t that satisfy this inequality actually obtain equality. That is, at t max, we get that a times vector v is equal to t max times vector v. So we're going to assume it doesn't. We're going to assume that we don't obtain equality, that it's still less than or equal to AV. We're going to multiply by a positive, strictly positive matrix on both sides, and so it actually gives us the strict inequality that a squared times v is strictly greater than t max times AV. What this ends up giving us is that if we make a substitution and let u equal this vector AV, right? So over here, we're gonna have this AV turns into a U, and we can take one of these A's out and it turns into this AV, which becomes our U again. We get this inequality that A times U is strictly greater than T max times U. So U serves as a candidate for the above inequality here, but we obtain a contradiction because we said that T max was the greatest of all the values that satisfies this inequality, this less than or equal to. However, since you have a strictly less than sign here for the right-hand side, what that means is there has to be some other value where we obtain the greater than or equal to sign again, meaning that T max wouldn't be the largest value, a contradiction. So as a result, we get that T max is the largest T that satisfies this, and through the contradiction, we obtain equality. By the definition then, if we obtain equality, it should be easy to see that T max is an eigenvalue of A, right? Now, what that tells us is that since A is positive and the entries in V are non-negative and it's not the zero vector, we can actually conclude that T max is strictly positive as well. So we've concluded it's a positive real number and we have that V is non-negative. But since T is now strictly positive, we can also actually determine that V is strictly positive because again, A is a positive matrix. And so since T is all positive, you're going to have both sides match up. V is not going to have any non-negative entries. So we have n eigenvalue and its corresponding eigenvector being strictly positive. Now we want to show that it's the largest of all of these eigenvalues. So suppose we take some arbitrary eigenvalue of a complex number and its corresponding eigenvector in Cn. Now, just for this proof, I don't want you to get confused, we're going to let the absolute value of z denote the entry-wise absolute value, right? And that is just to make the next statement. So we're not taking the magnitude, just we're taking the absolute value of each entry in z. What this tells us is that as a times z equals lambda z by definition, we get that the absolute value, if you take the absolute value of both sides, we actually obtain this inequality. Because taking the absolute value of A, for example, or the entry-wise absolute value, isn't going to change it since it's strictly positive. But it might actually change our vector z or our eigenvalue lambda, which can result in an inequality potentially. The idea is it'll always at least be bounded above by this. It'll never exceed it, right? Now, this inequality is very reminiscent of the one we just looked at, right? It's a candidate for t in this inequality right here. AV is greater than or equal to t times v. However, since again t max was the largest of all the values that satisfied this, we obtain that t max is already greater than or equal to any arbitrary lambda, or the magnitude of any arbitrary lambda, which implies it has to be our largest eigenvalue. So again, there's the Frobenius part of this theorem for non-negative matrices, and the proof follows very similarly, just making the distinction that if A is non-negative, we get a slightly different conclusion, and that is that for positive square matrices, our lambda max has geometric and algebraic multiplicity of just 1. Whereas for non-negative matrices, our largest eigenvalue may repeat multiple times, right? So it'll be greater than or equal to all the other eigenvalues as opposed to strictly greater than. So now let's tie up some loose ends. Let's give support to the claims of convergence that we made earlier in our definitions and in our operation with Markov chains, right? Because understanding the convergence of a Markov chain allows us to make a lot of important assumptions and understand key insights in any situation we look at. So what we want to show is that given a Markov matrix now, not just a positive matrix, but specifically a Markov matrix, that its largest eigenvalue is 1, and that we can define its corresponding eigenvector as the steady state distribution if P converges. So now I want to just recall that every column in P sums to 1. This is very important because if we take the transpose, then we know that now every row of the transpose sums to 1. And so because of that, we make the observation that PT, the transpose of P, times the 1 vector, where each entry is just 1, gives us back the 1 vector. And that's because if we just do matrix vector multiplication, row times column, we're always going to get, well, if we're multiplying by a bunch of 1s, we're just going to be summing each row, which again gives us a 1. And so it does that for all the rows, giving us the 1 vector again. By definition, then, we see that the 1 vector is an eigenvector for PT corresponding to the eigenvalue of lambda 1 equals 1. Now, what do we know? Well, given the characterization of the trace that we studied this semester, we know that the trace of a matrix is simply the sum of its eigenvalues. Now, the original definition of trace is simply the sum along its main diagonal, but we know that as each entry is at most 1, that the trace of our transpose of a matrix is going to be bounded above by summing 1 n times. So what does this tell us? This tells us that every other eigenvalue, if we have lambda 1 equals 1, is going to have magnitude at most 1, or strictly less than 1 if our matrix is strictly positive, right? So what we have then is our lambda 1 equals 1 is our largest eigenvalue, and since it's an eigenvalue of our transpose matrix, it's actually also an eigenvalue of our original matrix because they have the same characteristic polynomial. So as lambda 1 has at least one eigenvector, we then just define v1 to be the eigenvector corresponding to lambda 1 when it has geometric multiplicity 1. We won't have multiple v1s, if that makes sense. We only consider v1 in the case that lambda 1 has just one eigenvector. So now we have that v1 is an eigenvector of lambda 1 equals 1, but let's give claim or give support to the fact that we define it as our steady state distribution. That is, let's show that if a matrix P converges, one of these matrices P converge, it converges to just this matrix of just v1s for all the columns. So we're gonna consider two cases. First, let's start with positive matrices and consider two cases, but we're really only going to focus on the first one, and the second one kind of follows similarly to our reasoning here, where we're going to look at the case that P has n independent eigenvectors, v1 through vn. We know then if this is the case, we can diagonalize P as some x, d, x inverse, where d is going to be our diagonal matrix, where the entries are the eigenvalues of P. Then we know, it's very reminiscent, we can calculate the powers of P by simply taking the powers of this diagonal matrix and multiplying it in this product. So since P is positive, we know that every other eigenvalue, other than our eigenvalue of 1, is going to be strictly less than 1 through the Perron-Frobenius theorem, because lambda 1 equals 1 is our maximum eigenvalue we saw for these Markov matrices. What this gives us is that if we take the power of d to infinity in a limit, we know that taking the power of a diagonal matrix is simply taking the power of all the entries along the diagonal. But since this lambda 2 through lambda n have magnitude less than 1, these values are going to go to 0 as k goes to infinity. So we're just going to get this matrix of a 1 in the top left corner and zeros everywhere else. What that ends up giving us is that, well, first we just consider that the rows in X inverse are actually going to be the eigenvectors of P transpose. I have a proof for that if you really want to see why that's true. With each row corresponding to the same order of the eigenvalues we put in the diagonal matrix. So what that gives us essentially is that we know that in our P transpose up here, our first row is going to be this one vector just as a row vector, hence the transpose right there. And we know that these can be some other vectors, but they won't really matter because when we do this matrix multiplication, all these zeros are going to cancel out everything else other than this vector v1 times this one transpose, which in other words is just our matrix of v1 for all the columns, right? So that's what we want. So we see that for positive matrices with n independent eigenvectors, we're just fine. Diagonalization leads to this claim. However, we run into more of a problem if P doesn't have n independent eigenvectors, right? Because we see that there are lots of square matrices that simply don't have a diagonalization because of this. So all we have to do instead is consider its Jordan decomposition, right? If D is going to be our Jordan canonical form, we can just look at it as this notation right here where since we're always going to have the eigenvalue of 1, we're just going to put that at the top. And for positive matrices, it has geometric multiplicity 1. So it's just going to be a 1 by 1 block, right? And we're just going to leave all the other blocks and just denote it as this submatrix A, right? All the other blocks for lambda 2 through lambda n. So we know then that our first column for P, since our first eigenvalue is 1, our first column for P is again going to be this eigenvector V1. And likewise, the first row for X inverse is going to be the first eigenvector of P transpose, which we saw last time, which again was 1 transpose. So in utilizing this Jordan decomposition, we'll eventually just obtain the fact that, and again, I also have a proof for this, just not to take up too much time, but we'll just see again that if we take the limit of this matrix again, this Jordan canonical form, we actually also again obtain just this 1 matrix. And so as a result, we obtain the same thing even for this case of less than n independent eigenvectors, right? But it comes to the idea that when you take a power of a Jordan canonical form, especially with these ones with lambdas less than 1, these are actually going to keep decreasing just by the definition. So in other words now, we can say that for any initial distribution with positive matrix P, we know that y infinity exists, and we get that y infinity is just going to be P infinity times y naught, right? So we conclude that, given the definition of P infinity, y infinity is just going to be some multiple of our vector V1. So we've assured the convergence for every positive matrix. This means that in any Markov chain, if all of our probabilities are greater than 0, immediately we know that that Markov chain converges. That's an astounding result. Now, non-negative matrices are more case by case. It all depends on their eigenvalues. So if a non-negative matrix has its lambda 1 equals 1 having algebraic multiplicity 1, we know that its geometric multiplicity is also 1, and the convergence of such a matrix is assured. It'll fall into one of the 2 cases earlier depending on how much eigenvectors it has. However, if lambda 1 has an algebraic multiplicity greater than 1, we'll run into an issue because that means our matrix D, whether it's a diagonal matrix or a Jordan canonical form, will have more than just one value of 1 along the main diagonal, and thus we actually won't be able to obtain that matrix of just V1s for each column that we saw, so no steady state. Now, after looking at the theory, we're sufficiently equipped to understand these practical applications. So one thing we can use Markov chains for in real life is to model the probabilities and bond ratings. So suppose we have the following table for corporate debt, right? Where we have ratings of AAA, AA, single A, B, and C, and these are the probabilities of going from each one. The way we read these probabilities in a Markov chain is we read from column to row, since our columns sum to 1, right? So in other words, what this is saying, for example, is that like if I start at AAA, or if my company's AAA, there's an 80% chance of remaining in AAA for the next year. Or for example, let's say a 10% chance of going to AA, or a 1% chance of going to C. So we saw now, and we're confident that we can store these probabilities in a Markov matrix, right? And we can pose some questions. So say we have a company is currently rated single A. What's the probability that it will be rated C 5 years from the present? So then what this gives us is we have some initial distribution where we have the companies 100% rated single A. You know, we read this as, just as we have in the matrix, we have AAA, AA, single A, B, and C. So the company starts single A, so it's 100% single A. We calculate Y5 through the transition equation we saw earlier, right? So Y sub 5, or our distribution 5 years from the present, is just going to be our probability matrix to the power 5 times our current vector. Approximating this gives us these values. Even though we had to approximate, they were still better than some of the values we had to calculate for the midterm. But basically, we get that the probability that this company is rated C 5 years from now is about 21.3%, looking at this last entry here, right? So if we're looking in general, we're trying to see the trend of the Markov chain, we're going to want to look at the steady state distribution, or the eigenvector V1, and we get that in the long run, most of our companies are going to end up C, as this probability is going to be greater than all the other ones, right? So regardless of our current rating, what this eigenvector tells us is there's the highest chance of just going to be rated C after a really, really, really long time. We can make other applications in finance, for example, modeling the probabilities of certain financial market climates, right? So we just define some terms. A bull market is a period of time where the stock prices seem to be generally rising, a more optimistic way of looking at it, whereas a bear market are periods of time in which stock prices are generally declining, or a more pessimistic way of looking at it. Whereas then we also have stagnant markets where it's not really going anywhere. It stays kind of in the same spot, neither increasing or declining. So let's just assume that to implement a nice example with Markov chains and something not as complex, let's just assume that market information is distributed equally, so no one has an upper hand, and stock prices fluctuate completely randomly. Let's start with an example. Let's suppose these probabilities just so we can see then how Markov chains can apply to such a situation. So we have these probabilities for bull weeks, bear weeks, and stagnant weeks. For example, there's a 7.5% chance after a bull week that a bear week will follow, and so on, right? As we have these all of these probabilities here. We play the same game where we can draw a diagram. Maybe if any of you guys are familiar with biology, this is unintentionally reminiscent of something, and calling it a flow diagram doesn't help. But the idea is that we can represent these probabilities inside of a diagram, and the diagram helps us then to make the matrix, right? And we have all of these probabilities encoded here. An insight we can make is that since all of these entries are actually positive, we can already be certain that this converges to something, right, as we saw earlier. So we find the eigenvector corresponding to lambda 1 equals 1 for this matrix yet again, and we get the steady state distribution, which is going to be 1/16 of this vector right here. So we just factor out a 16th in this case. What this tells us is that given our probabilities, just for the example, at 62.5% of all weeks will be bullish, 31.25% will be bearish, and 6.25% will be stagnant. So the idea is essentially we can just apply Markov chains to a lot of financial examples, and it allows us to make some really key insights and key claims about situations that we're looking at.
Another one of the most common forms of applications for Markov chains is in models for infectious disease. One of the most famous of these is the SIR model, which stands for the susceptible, infectious, removed. Now the SIR model, it's an epidemiological model that displays the theoretical number of people infected with a contagious illness with the two following things: that one, it must be a closed population, and two, it gives the understanding of a permanent immunity. So looking at the diagram, what it means is that we have our three states: susceptible, infectious, and removed. So people in the susceptible state at any time can either remain susceptible or go to the infectious state. Likewise, people in the infectious state can either remain there or go to the removed state. But at no time, anyone in these states can move left on this diagram. That's why there's the one-directional arrows. Also note that the removed state is going to be composed of two different groups of people. One, the individuals that were infectious and then recovered, and then given this model they have permanent immunity. So they have no other effect on the other two states. Or if they were infectious and didn't make it and passed away, then either way they would be considered removed from this model as they have no other impact on the other states. So in these SIR models, we model them with the following, where S of t is the percent of susceptible at time t, I of t is the infected at time t, and R of t is the percent removed at time t. So given these following differential equations, we can always figure out the change in the percent at any time t. ds dt will equal negative alpha times S of t times I of t, and di dt will equal alpha times S of t times I of t minus mu times I of t. In both of these examples, alpha is just an infection rate parameter, and mu is just a recovery rate parameter. So if we look at this graph, it gives us an example of kind of what's going on here, right? Most of the population in this example is just starting off susceptible. And then over time, the population begins to get infected. And then eventually, if you go on far enough, everyone ends up in the removed state, meaning that, as we saw earlier, it's an absorbing state. Infinite discrete Markov chains, they're particularly useful, especially in SIR models, and they have several assumptions that we'll be considering while moving forward. The first one being that the current state of an individual is dependent only on the state of individuals at the previous time step. We already knew that by just the definition of Markov chains. And then no individual at the removed state can be susceptible or infected. And lastly, the transitioning probabilities are independent of time and remain constant over the time of the study period. Now this last step isn't always the case in epidemiological models, but it gets really confusing and complicated with complex equations to model it. So for the purpose and for the time constraints that we have here, we're just going to go with one that has the same transitioning probabilities. All right, so we see here that all that is needed in order to utilize these models is two things. The first one being a transition probability matrix. And we see just based on the arrows and how certain people can't go to other states, we can already identify several of the entries as zeros and ones. And then the second thing we need is an initial state y0. So there was a study published by Hindawi, and the transition probabilities, the probability matrix for hepatitis B was found to be this matrix here that's up on the board. And so this means that given any state y of 0, we were always able to predict, or in that case, they were always able to predict the future cases of hepatitis B. So if we just let our initial distribution be 0.9, 0.1, then we can multiply it by our matrix and find the distribution at the next state. Likewise, we can do that again and again. And if we go on forever, as mentioned before, we'll end up with everyone in the removed state. So that SIR model might seem kind of trivial and not too useful, right? We see a lot of these other complex models of epidemiological models can be really useful for the following things. They're really good at assessing epidemic spread. They're really good at modeling the pace at which an infectious disease is spreading. And by knowing the pace, we can predict a lot of other factors such as needs. One of them being hospital capacity. I know in the past few years it's been a big issue that a lot of hospitals have been overflowed with COVID-19 patients, and they've run out of beds. And so the Markov chains were actually used to be able to predict hospital capacity needs in order to get in temporary beds and temporary shelters in order to accommodate all the patients. And lastly, they're really good at predicting the rate of travel of diseases between different geographical locations.
All right, so for our last application, this one will be a bit more, I guess, personal, right? So when searching the web, there may be millions of suggested websites. How do we find the ones we care most about, right? And over here we have a screenshot of a search for Andrews University. And as we expect, the site we're looking for, Andrews University, is all the way at the top, as opposed to something like Southern being there, right? So what we want is we want to return the requested page in order of the user's preference, and we want the first 10 pages, that is the first 10 links to be returned, should be the most popular as well, right? So Google co-founders Larry Page and Sergey Brin's PageRank algorithm does just that, right? So a bit of history, it was developed in 1996, utilized 2 years later in the Google search engine, and is not the only algorithm used, but the most popular and was also the first used. So how does it work, right? The PageRank algorithm determines a rough estimate of how important a website is by counting the number and quality of links to a page. If your page is being linked by multiple websites, then it must be pretty popular, right? And we also assume that more important websites are likely to receive more links from other websites, as I just said, right? So the formula for the PageRank, PR of a page PI, is given by the following. And I know it looks pretty complicated, but we'll go through each part right now. Where D, also called a damping factor, is the probability that a user will continue to randomly click on links. And through their research, they found that D equals 0.85 was a good starting point for that. And we also have pages P1, P2, all the way to Pn. Those are the pages we're considering. M of Pi is the set of all pages that link to Pi, that point to Pi. And O of Pj is the number of outgoing links on page Pj. That is the number of links that all point out to some other website, right? So note that each page is initialized with a page rank of 1 over n, where n is the total number of pages. We do that so that every page gets like a fair chance of being like the most popular or going to the top, right? If PR of page PI is equal to 0.42, there's a 42% chance that the user clicking on a random link will reach your page PI. And lastly, all our page ranks sum to 1, because this is a probability, and this was also demonstrated through their research as well. So how do we compute PageRank, right? Well, we have this iterative computation. And if you glance at it, you'll see that this is actually essentially the same thing, the same formula over here, just translated into linear algebra, right? And one note, that each entry in this matrix G over here is 1 over the outgoing links of Pj if Pj links to Pi, and it's 0 otherwise. All right, so let's go through the following example. Consider this example where you have page P1 is pointing to pages P2 and P3. P2 points to P1 and P3, and P3 points to P1. So here our total number of pages is 3. Hence the initial state of page ranks is given by the following vector over there. And if we calculate the first instance of page ranks, we have those values over there. Similarly, the next instance will be given through that calculation, and we see it's that vector over there. And we can continue this on forever, and this last vector over here is the final page rank of our system. So this isn't the final page rank, this is the final page rank. If we continue this process forever, we land at the final page rank over there. What if instead we begin with this following initial state vector, right? Where instead, for some reason, we start with page 1 having a probability of 0.1, page 2 with 0.5, and page 3 with a 0.4. So if we calculate the first instance of page ranks, we see that they actually differ from what we saw earlier. But if you continue on forever, you actually get the same thing. Is Markov hiding? Of course he is, because this is a Markov chain talk, right? So recall our previous example where we have our G matrix and our diagram over there. So notice that if you look at this entry over here, this represents the chance that page 2 goes to page 1. And notice it's half, because page 2 can go to either P1 or P3, right? Likewise, the chance that the page P3 goes to 1 is 100% because P3 only points to P1, right? So we can label the probabilities as following, and this should look pretty familiar, right? It turns out G is actually a Markov matrix, right? And this is actually a Markov chain. And we can see the Markov chain through this iterative computation, right? So notice that the next state of PageRanks is dependent only on the current state, right? So Google's PageRank algorithm is indeed a Markov chain. We have a list of references, and I just want to say thank you.